Alright, welcome to another AQA A-level chemistry video. Today I'm going to be making a video on the part 2 on exam questions on this acids, bases, and buffers. Now, these two questions that I have today are related to mostly buffers. I'm keeping it concise to two questions only, because I think maybe the last video was too extended or too long. But you guys got to remember, I'm just doing all the questions that are related to acids and bases, but because I want to cover all of the ones that before I start doing exam questions, so I'm going to cover all of them. Now, I've done only two questions in this one, but I've left the timestamps for the questions that related to, what you want. If some of the questions are too easy for you, just go and do the questions that you need to do. But apart from that, I'm going to start this video off, and hopefully this is more these two questions aren't too difficult, but I wanted to give you guys, all the types of possible questions that could potentially come up. These two questions are ones that I've made up, but there's no reasons why they couldn't come up in the exam. Well, this first one isn't. But anyway, I'm gonna stop waffling now and actually just get straight into the video. So, question 6. So look at this graph below, right? I allow you to look at it, examine it, right? So we've got two different graphs, two pH graphs here, and we have the different types of buffers. So different types of indicators, as you can see on your left here. So on your right, sorry, my bad. On your right you have different indicators, and on your left you have two types of pH graphs, right? So based off of the information allocated, based off of the information that you have here, I want you to allocate the correct letter that corresponds to the right indicator for the two titrations above that you believe would work best to detect when the reaction has come to completion. So all this is saying here, right, is... Actually, no, I think you can read this. You can read that and understand what I'm trying to say here. So if you've read the information, I want you to try and attempt to answer this question. So pause the video now and try and answer it. If you pause the video now and you try to answer it, I assume you've understood. If you didn't make any sense, I'm pretty sure that made sense. But if it didn't make sense, I'll say it out here. All it's saying is, these are your indicators here, right? So these are your indicators here. And they're all labeled by a specific letter. P, Q, R, and S, right? I want you to put down the letter of the indicator that I want you to put down in this box here and this box here the letter of the indicator, or the letter that represents the indicator that will be best suited for that type of reaction. And if you only got that what I meant now, then put that in now. Alright, so for this first one here, this is clearly I tried to do it other way around because everyone knows that for most examples it's an acid base titration. So I decided to do a base acid titration where we're adding acid to our base that's in our conical flask, and the acids in our purette. Because there's no reason why it wouldn't come up. But if we're clearly titrating a weak base with a strong acid, in this first example here, and we're trying to look at the indicators that would be most useful for this type of reaction here. So if we're using a weak base and a strong acid, our equivalence point is somewhere in this region here, right? So that instantly tells me alizarin yellow is definitely off the list. We can't use that because we don't have a strong base. Phenolphthalein is probably not the best one to use because we're definitely not the best one to use because it's not within that. Phenolphthalein is more for stronger base. It's weak bases, but could it work? This base in particular, probably not. I wouldn't look at it. The ones that I'd look at the most, you have to look between this range here, because 8.2, sorry, 8.2 to 10, so phenolphthalein wouldn't work. You're looking at anything between 8 and anything above, say, a 2, and anything below a 8. And so if you put either R or S, you'd get the mark here. They'd usually allow both. So if you put ROS here, ROS, you'd get the mark. Just make sure it's not P or Q. For the second one here, I'd look at, so now we're titrating a strong base with a we're titrating a strong base in our conical flask with a weak acid. As you can see here, very high, it starts with a very high pH. Equivalence point is anywhere from 13.9 really till 16.0. So really here you could use either P or Q. Now there are more specific examples. I've only done two here, but the point being is that you can see what's going on. There may be an example where only one indicator will be the best one to use. I'm going to change that. And this probably isn't the best because I've used the two. So there is a few examples where you can use there's two possible answers. But the point being is that you can clearly see here why methyl orange wouldn't be useful, because its pH changes at a pH that's too low. The indicator here for bromothiamyl blue changes color at a pH that's too low. 6.0 is a bit too low. And so the ones that you'd want to use here are phenolphthalein and alizarin yellow. Either one of those two will be fine. So you can put P or Q here. Alright, so now let's go on to another question here. So if we look at the equation below relating to an acidic buffer, including the use of the two equilibria reactions of the dissociation of propanoic acid and its salt, sodium propanoate, I want you to explain the purpose of the salt in the buffer. Now, I say all this information given the fact that you've watched my video on acids and bases and buffers. So if you can understand how to answer these questions, because I think this is questions that you could probably answer yourself, right? In relation to equilibria and buffers, I want you to try and answer this question by yourself. So pause the video now and try and answer it yourself. Alright, so I've assumed you've tried to pause the video now and try to answer it yourself. The first question may be a bit hard for you to understand because you probably don't know the right terminology to use, and you probably will. If you've heard of, I probably should have taught conjugate bases now that I think about it, but I mean, would I teach conjugate bases? No. You ask your teacher about conjugate bases. I'll probably do it. If you really want me to talk about conjugate bases, leave a comment in the comment section of this video, and I'll go through it. But I assume the majority of people know what a conjugate base is. So, so the first question here is explain the purpose of the salt in the buffer. So, the purpose of the salt in the buffer is that it provides a stable form of a conjugate base in case any acid is added. So, I'll just say it here. It provides, what did I say? A stable form of a conjugate, and in case you're wondering what the fuck I'm talking about, I'll go through it again. So it provides a stable form of a conjugate base. In case any acid is added. And this is for the part A, right? So what do I mean by that? What do I mean by provides a stable form of a conjugate base in case any acid is added? What I mean by this, hopefully my handwriting isn't too broad, but it probably is a little bit. It's because here this salt, right, it dissociates. So we know that so it provides a stable form of conjugate base in case any acid is added. We know that this is that salt. This is a salt. So salts fully dissociate in solution. So here we have we have a weak base, right? Weak bases weakly dissociate H plus ions in solution. So they weakly dissociate in solution. So therefore we know we have a high concentration of propanoic acid in comparison to propanoate in from this dissociation, right? And a low concentration of H plus associated. But because the equilibrium is not very far to the right, it's more closer to the middle, whereas what's it called? Sodium propanoate is a salt, so it fully dissociates in solution. So therefore, we expect to have a high concentration of propanoic acid from this dissociation, and a high concentration of the sodium ion. That's more of a spectator ion, if I'm being really honest. That's not really the most important part. And we'd have a low concentration of sodium propanoate as in the unionized form in a solution in comparison to sodium propanoate, and in comparison to our propanoate ion and our sodium ion. And I said it's because in this case equilibrium is far to the right because salts fully dissociate in solution. So there's a high concentration of propanoate ions in comparison to unionized sodium propanoate. I want to speak a bit louder, but it's kind of night time right now, so I don't want to make too much of a noise. That's why my voice is a bit low and I'm probably a little bit not too exciting right now. So please bear with me. But the point being, right, is that we want to have enough of this is the main part of a reaction, right? This here is the main part of our reaction, right? But there's already a problem here. There's not enough of it. If we wanted to control the pH of this reaction, we need to have enough of base in case, say that we had too much acid, right? And we need to if think about it, if you're having an acidic buffer and it's all of a sudden pH is a bit too high, how are we going to counteract that if we're going to usually counteract it with base, right? Some sort of basic property. This is our only basic property if we're not including this, right? If we discredit this whole reaction here, right? And we only had this reaction here, right? And say that there was an increase in sorry, did I say increase in base? I meant increase in acid, sorry. Say that there was a massive increase in acid, right? You usually counteract the acid with base. So if say the pH went down lower than you'd expect, you wouldn't have enough base to neutralize the acid. And you can't, and this is a weak base, so it can only dissociate a certain it's gonna weakly dissociate H plus ions in solution, or weakly dissociate in solution. So you're gonna remain with a low concentration of propanoate ion and low concentration of H plus in solution. So to counter this, what we're gonna do is that we'd introduce a salt of that weak acid. And the same thing applies to the bases, right? But salt of the weak acid, because we know salts fully dissociate in solution. We don't care about the H plus. The H plus is one that we can control. That's fine as it is. But what we need is more propanoate ions. The propanoate ions are the ones that act as a conjugate base. So they're the ones that will kind of like weak bases that will react with the acid, and therefore neutralize, right? Because salts fully dissociate in solution, we're going to have a very high concentration of propanoate ions in. But by the way, both equations are happening in the exact same solution. So we have a high concentration of propanoate ions dissociated from this reaction. So therefore, we have a high concentration of propanoate ions in our solution in cases that increase in acid in our solution, right? And that's all it is. That's all it represents. it just makes sure that it provides a stable form of conjugate base, or a stable concentration of conjugate base in case any acid is added. Hopefully that made sense. Right, so I'm going to cancel all of this now because... So the next part here is, right, explain how in this buffered solution a constant pH is maintained when there's an increase in acid solution. So this is a 2-mark question. Explain how this buffer solution is constant. Sorry, let me repeat myself. Explain how in this buffer solution a constant pH is maintained when there's an increase in acid in our solution. So when H plus concentration increases, by the way, I assume you've already tried to answer all of these questions already, so I'm just answering over again. So when there's an increase in H plus concentration in solution, right? So it's no longer low, it's high. Or I'll use this color instead. It's now high. The higher than we'd expect. What does that mean? So how do you actually... So the first thing I say is that there's an increase in H plus concentration in our solution. Just mentioning that I haven't got the mark scheme with me, but something along the lines of mention that H plus concentrate is an increase in H plus concentration in our products. This causes equilibrium to shift to the left. Okay, that's the main thing. Saying equilibrium shifts to the left, or saying that there's an increase in concentration, there's an increase in H plus concentration in our products, causing a shift in equilibrium to the left. That's 1 mark. So I think that one's here. So for part B, there's an increase in H plus concentration, causing more H plus to react. So causing equilibrium to shift to the left, sorry. Causing equilibrium to shift to the left. And then you say to react with propanoate ions to reduce, by the way, if you want to just skip to the answer, I get it, but I'm just reading it out for you guys to understand. So to react with the propanoate ions to reduce H plus concentration. Okay. So to react with the propanoate ions, don't write this as I'm doing it because I might make a couple of mistakes. I'll write it when I've fully completed my answer. So to react with propanoate ions to form more propanoic acid to reduce the H plus concentration, right? So the first part, the first mark is for mentioning that an increase in H plus concentration causes equilibrium to shift to the left, right, which will then react with the propanoate ions to form more propanoic acid. And then the second mark is mentioning that to reduce the H plus concentration. To return pH back to a constant pH, constant acidic pH. again, look at, if you ever got these mark schemes, there's probably, I haven't got a mark scheme with me, so I'm just going straight off the top of my dome, and that's the main points I'd be looking for. This is just, treat this question like you would for any type of equilibrium questions. It's just an equilibrium question, but I'm not mentioning the fact that it's equilibrium. I'm talking about pH here. But really, the pH is altered by the H plus concentration, and or the basic concentration, right? And that's all you need to mention. So now that's happened, right? We've now got returned back to a position here where the pH concentration has been, the H plus concentration has been lowered, and it's gone back to low, and that's what we want. All right, so explain how the buffer ensures a constant pH is maintained when there's an increase in base to our solution, right? Now, it's fair to, they usually mention the type of base. Again, I just made these questions randomly. So they usually mention the type of base that you use. So it'll probably be some sort of strong base, like a sodium hydroxide, right? So I'm going to make, probably should have said this in the question, but as you can clearly see from this video, I'm clearly just YOLOing it. I'm just YOLOing it. This is not this is probably not one of my best videos I've made. It's really late at night now, so please just bear with me. But if they usually name a base, so it'll be some sort of sodium hydroxide. If they haven't mentioned it, it is fair to assume that it'd probably be an OH minus hydroxide ion. So explain how the buffer ensures a constant pH is maintained when there's an increase in base to our solution. Increase in base, so an increase in OH minus to our solution. Right, so the first thing I'd notice is that if we want to reduce this OH minus in our solution, right? How we're going to do that? We're going to get it to react with, the H plus to form water, right? But if we do that, we're reducing our H plus concentration. So what actually happens is equilibrium will shift to the right to dissociate more propanoic acid to then increase the H plus concentration that's been decreased. I'll say it again if it hasn't made any sense to you, right? I'll say it because maybe it doesn't make any sense. I'm going to go back here again. Delete this. I'll delete that. I'll delete that. I'll delete all of this. I'll delete all of this here. Right. So we have an increase in hydroxide ions in our solution. That's what's happened, right? So therefore, what happens is we want to reduce this hydroxide concentration. So the hydroxide ions are going to react with the H plus. When it does so, it will form water, which is great because now we've neutralized base in our solution. We've now removed H plus. We've removed, assuming that there's more H plus in our solution than hydroxide ions. We've now completely depleted the hydroxide ions in our solution. But now we have a problem now because we've now decreased the H plus concentration in our solution. So it's no longer the pH that we once had. Remember, this is an acidic buffer. This is an acidic buffer, so we want to maintain a constant pH, a constant acidic pH. If we're reducing the H plus concentration, we no longer have that constant acidic pH. So now we have a problem, right? So we've neutralized the hydroxide ions by reacting with H plus to form water, but in doing so, we've reduced our H plus concentration. So how are we going to increase our H plus concentration to get it back to the concentration that we originally had? Well, what will happen is if there's a decrease in, remember this is an equilibrium, right? This whole thing is an equilibrium. So if there's a decrease in H plus concentration, the way that we'd increase H plus concentration is having equilibrium shift to the right to dissociate more propanoic acid to propanoate and H plus to increase the H plus concentration. So the first thing I mentioned, right, is saying that an increase as I was mentioning that there's an increase in hydroxide ions in our solution. Will I mention that? How do I go about saying this? Yeah, I go about saying H plus ions reacts with any hydroxide ions that have been added to our solution. There's an increase in hydroxide ions in solution. H plus ions will react with any hydroxide ions in solution to neutralize base or to form water and neutralize base. That's probably the first thing. So then equilibrium will now shift to the right. You can put in bullet points, by the way. I advise doing bullet points. Equilibrium will shift to the right. To dissociate. That's that right? To dissociate. More propanoic acid. In solution to increase H plus concentration. And that's it. I apologize for this video. It's probably not my best video. I have to be really quiet because my parents are asleep right now. So, yeah, but that's it. Hopefully this video was helpful to you and explained it well enough so that you can understand. And that is it. So